Phi 1? No. So when you add these two, you get 2 phi 1, then minus phi 2 minus phi 3. And when you subtract, what do you get? You get something multiplied by I, but you just divide by I. Subtract and divide by I. What do you get? You got the sign wrong, Anup. Root 3 is common, phi 2 minus phi 3. Okay, so these are the SALCs. If they are to be molecular orbitals, they should be normalized, right? What is the normalization constant for this? Phi 2 minus phi 3? 1 by root 2. What is the normalization constant for the first one? 1 by root 6. Don't forget the 2 in the beginning. I think there are questions, please ask.
After subtracting, I is remaining.
That's why I am dividing by I.
Can I divide by?
Yeah. See, our whole purpose is to just convert to something that is real. I have to divide by I. I can do whatever I want. I can add, subtract, multiply, divide by constant. I is a constant. Any other question? Are you convinced? What happens if you add? What do you get? Phi 1 plus phi 1 is 2 phi 1. Then you get epsilon plus epsilon star phi 2 plus epsilon plus epsilon star phi 3. Isn't it? And epsilon plus epsilon star is minus 1. That you worked out a little while earlier. That is why you write minus 1 here, minus 1 here. And when you subtract, what happens? Phi 1 minus phi 1 is gone. Then you have epsilon minus epsilon star multiplied by phi 2. Yeah. And minus epsilon minus epsilon star multiplied by phi 3. Whatever, you can put the minus in front of any one, doesn't matter. So this is how we generate the MOs. And why am I calling these the MOs? Because in this stage, they were actually linear combinations of all the atomic orbitals. Alright. So this is a simple example by which what we have learnt is, we have learnt how to handle a little big molecules. It is only a 3 atom molecule, I agree, but 3 is more than 2, isn't it? Yeah.
So you're saying these are the two MOs.
Yes.
Just yesterday we talked about orthogonality. So
Work out if they are orthogonal or not. Multiply them together and add. What do you get? Phi 1 of course won't even come. Are they orthogonal or not? Please multiply. The answer is not written anywhere. You have to work it out and see. Please multiply 1 by root 6 into 2 phi 1 minus phi 2 minus phi 3 by 1 by root 2 phi 2 minus phi 3 and see whether you get 0 or not. Remember that phi 1, phi 2, phi 3 in themselves are orthogonal. Do you get 0 or not? Are we getting 0? What about phi 1 plus phi 2 plus phi 3 and 2 phi 1 minus phi 2 minus phi 3? Are they orthogonal? Nishit?
Coincidental that we added and subtracted and we got orthogonal.
It is not coincidental, it is a result of experience. Right? We see further because we stand on the shoulders of giants, remember? So giants have worked it out for us. And the logic is that you are going to get E double dash when you combine these two irreducible representations corresponding to E. Right? And there are only two ways to combine, add and subtract. So what this does is this saves us a lot of trouble, because if you want to generate by actual symmetry operation and all, what will happen is you are going to end up with not the actual LCAOs but their linear combinations. I skipped that part. Please go through Cotton's book. They have done it that way. By using the full D6H group, they have worked out, they have seen what they get. They do not get these two. They get linear combinations. Well, they get first one, they don't get the second one. And then you have to do it by brute force method, trial and error, and find the last one. That is not such a happy situation. Okay. So this is something that saves us a lot of trouble. Okay. So let me, this page is a little cluttered, let me write this on a little fresh page. What are the orbitals we said? I will write it like this, maybe psi, I will write psi. Psi A2 double dash is 1 by root 3 phi 1 plus phi 2 plus phi 3. If I want to sketch it, and instead of drawing it in such a weird manner, I like to draw it like this. Okay. The plane of the paper is the molecular plane. These circles are p orbitals, you are looking down upon them, not in the figurative sense. Do not look down upon orbitals, they are extremely useful, right. So, you are looking down from the top. If it is plus, then it will be filled. If it is minus, then it will be hollow. Okay. So, do you agree that this is a depiction of phi 1 plus phi 2 plus phi 3? Now, next one, psi E double dash, I will put the subscript here, 1. What is it? Let me write the simpler one first, 1 by root 2 phi 2 minus phi 3. Now, if I want to draw it, maybe let me put the numbers here 1, 2 and 3. Can be anything, does not matter, 1, 2 and 3. So, if it is phi 2 minus phi 3, what should it be? In 1 I do not draw anything, right. Phi 2 is plus, this is minus. The third one, psi E double dashed 2, that is equal to 1 by root 6 2 phi 1 minus phi 2 minus phi 3. What will it look like? Let me write the minuses first, minus phi 2 minus phi 3, and maybe I will draw a bigger circle. Even though it is not, so this is easier to depict if you look from side. You just draw a p orbital that is double the size in length, not width. Okay. So, what have I done? I have generated the molecular orbitals. How many nodes are there in each? 0, 1, why 2? 1, 0, 1, 1, isn't it? This is one node, this is one node. Where is the node here? There is no node. Here, node means wave function changes sign, right? And here there is nothing, so there is no question of changing sign. So, wave function changes sign from between here and here. And here also, wave function changes sign between here and here. Once. See, from here to here, there is no change in sign. From here to here, there is a change. From here to here, there is a change. But then, that is depicted by this one plane, one nodal plane. That same nodal plane serves to separate the thing. Or you might want to draw it like this. If you now look from that side, okay, what do you see? You see one big p orbital, okay, and let me draw it like this. These two are of the same sign, isn't it? So I can mix them and I can draw it this way. This is above the plane, this is below the plane. Now do you see there is only one plane? This is one, this is one, this is one, right? This is your 2 phi 1 minus phi 2 minus phi 3. It's just that this should have been really long, double the size. So see, here to here there is no sign change. This is the nodal plane, isn't it? There is only one nodal plane. It is not here to here and here to here. These two have mixed, right? So there is only one nodal plane. Got it? Do you see only one nodal plane? How will I put my hand there? Yeah, like this. Do you see only one nodal plane? This is your 2 phi 1, this is minus phi 2, minus phi 3. This is the nodal plane. Right? Are you all okay with this? Only one nodal plane. And what was the other one? The other one is like this, phi 2 minus phi 3. Where is the nodal plane? Here. Right? So now we have reached something that we must have studied at some stage or the other, right? What we do as a rule of thumb is that we correlate energy with the number of nodes. So see, this one psi A2 double dash, that has no nodal plane, no node. So if you plot energy qualitatively, this is where it is going to come, right? And I will even drop psi, I will call it the A2 double dashed molecular orbital. And then will you agree with me that psi E1, psi E double dash 1 and psi E double dash 2, they would have the same energy? Both have one node each, so they will occur together. Let me draw it like this, and I will call them the E double dashed degenerate set of wave functions.
They have same node, but their compositions are different.
Doesn't matter.
Then the energy will be same.
So to answer that question, what do we need to do? We need to perform a full Huckel treatment. We have to get to the secular equations, solve the secular equations and see. But qualitatively, this is what I have to say. We know from our very basic studies that degeneracy and symmetry go hand in hand, right? You have studied particle in a box, two-dimensional box. For a square box, 1, 2 and 2, 1 states are of same energy. For a rectangular box, 1, 2 and 2, 1 states are of different energies, right? Degeneracy and symmetry go hand in hand. In a free metal ion, all the 5 d orbitals have exactly the same energy, they are degenerate. You put it in an octahedral field, they will separate into T2G and EG sets, right? So EG sets are still, the orbitals in EG set are still degenerate between each other, they will have one kind of energy. The 3 orbitals in T2G will have one kind of energy, right? Now you bring in Jahn-Teller distortion. Now what will happen? What happens in Jahn-Teller distortion? Degeneracy is lifted further, isn't it? So that is something that we know from very basic studies. So far let us be happy with that, but let us keep this. We are going to discuss your secular equations also. We should work this out and satisfy ourselves that these 2 orbitals indeed have the same energy. All right? Okay. How many pi electrons are there? 2. Where will they go? So, what will the configuration be? If I now want to write electron configuration, yes, A2 double dash 2. So, this is a situation where occupied molecular orbitals are completely occupied. Whatever molecular orbital is occupied completely, right. So, this is a state, right. Electron configuration defines state, all right. So, this state is called a totally symmetric state. When occupied orbitals are completely occupied, then the state is a totally symmetric state. For D3H, what is the totally symmetric state? D3H, what is the totally symmetric state? A1 dash. Here, A1 dash. So, this state, this whole thing, this configuration, it is called an A1 dashed state. State of what? A1 dash state of what? The molecule, not the electron. Understand what I am saying? That is a rule of thumb. This is something that is discussed in very great detail in Harris and Bertolucci's book. Rule number 1, rule number 2, rule number 3, they have up to 6 rules. The first rule is that when all the occupied orbitals are occupied fully, then the state is a totally symmetric state. So, we call it an A1 dash state. To answer your question, it is not exactly a rule of thumb, you can work it out. So, what do you have? You have A2 double dash square, right. So, one is A2 double dash, second is also A2 double dash, right. Do not add, multiply. Oh. If you take a direct product, you cannot add, you have to multiply. What is A2 double dash cross A2 double dash? Without looking at the character table. Huh? Yeah, it has to be the totally symmetric one because you are multiplying it with itself, right. So, wherever you have plus 1, you will have plus 1, wherever you have minus 1, you will have minus 1, plus 1 into plus 1 is plus 1, minus 1 into minus 1 is also plus 1. So, when you multiply something with itself, you get the totally symmetric state. That is why we call this state the totally symmetric state, all right. What happens when an electron is here? Let us say now you have brought in some light and you have promoted an electron from A2 double dash molecular orbital to one of these E double dash orbitals. What should it be? It should be, no, forget about singlet triplet, that comes later. It should be A2 double dashed cross E double dashed. Work it out, A2 double dashed cross E double dashed. A2 double dashed cross Are you getting E dash? Everybody is convinced? I haven't worked it out myself, but if you are getting E dash, then we are a little lucky. Generally, it does not work out like that. Generally, what you get is a reducible representation which breaks down into multiple terms. But if you are getting it, it is fine. Work it out. You are getting E dash, so you are lucky. What will we call that state? E dash state, right? And then, depending on what is the electron, what is the spin wave function, it can be a singlet state or a triplet state. Okay. So, what is it that you get? Is it a singlet state or a triplet state? Why is it a singlet state? No, don't work like that. Work like this. You know Pauli principle? What is Pauli principle? No, that is Pauli exclusion principle. And there are also watered down Pauli exclusion principles simplified for high school kids. What is Pauli principle? Yeah. Pauli principle states that the total wave function for a fermion, say the whole thing. Total wave function for a fermion like electron. What is a fermion? A spin half particle. Fermion is not antisymmetric. Fermion is a spin half particle. The total wave function of a fermion has to be antisymmetric. Right? Antisymmetric. So, antisymmetric with respect to what? Exchange of particles. So, what are the spin wave functions possible? Alpha and beta, right? And how many wave functions can you write out of them if there are two electrons? Electron number 1, electron number 2. Electron number 1 is in alpha spin, electron number 2 is in alpha spin, in beta spin. Okay, first is both are alpha. Alpha 1, alpha 2, that is possible. Is it symmetric or antisymmetric? Symmetric. Can I use that here? Because your spatial part is symmetric, right? So if you multiply that by a symmetric spin part, then you get a symmetric total wave function. You cannot use that. So alpha alpha is not allowed. Alpha beta is not. Beta beta is also not allowed. What about alpha beta? Alpha 1 beta 2. Alpha 1 beta 2 is also not allowed because electrons don't have numbers written on them. They are indistinguishable. So you have to write alpha 1 beta 2 plus beta 1 alpha 2 or alpha 1 beta 2 minus, we are all clear about this, right? Alpha 1 beta 2 plus beta 1 alpha 2 or alpha 1 beta 2 minus beta 1 alpha 2. Which one of these is antisymmetric? Our quest is for an antisymmetric wave function. Both are linear combinations. The linear combination with minus sign. So that is the only spin wave function that survives, isn't it? So what will be the total wave function then? The space part multiplied by alpha 1 beta 2 minus beta 1 alpha 2. So there is only one total wave function that is possible, right? So we call this the singlet state. Singlet A1 dashed state. When I write a singlet as a superscript before the letter, do not read it as 1. It is not 1 A11 state. It is singlet A1 dashed state. Okay. Not from symmetry exactly. We had to invoke the Pauli exclusion principle, Pauli principle rather, which says that the total wave function has to be antisymmetric, right? So now, for a 2 electron system, the wave functions that are possible are alpha alpha, yes. Alpha alpha, beta beta, alpha beta plus beta alpha, and alpha beta minus beta alpha. See, all these three are symmetric with respect to particle exchange. This is a unique wave function that is antisymmetric. Okay? So if you are dealing with a fermion like electron, and if the space part is symmetric, then this will be the only spin part that will be allowed. So you understand what I am saying? So if you are dealing with electrons and if the space part is symmetric like what it is, then only this spin part is allowed, right? So that the total wave function is antisymmetric, then it is singlet. Now suppose the space part is antisymmetric with respect to particle exchange, then what will happen is that all these three will become allowed, right? So for one space part, you will have 3 spin parts. So you will have 3 total wave functions. That is the meaning of triplet. Singlet means 1 wave function, triplet means 3 wave functions. That 2s plus 1 is another example of chemical jugglery with numbers to get the right answer. No, not exactly, there is a question of degeneracy, but this is what it means. Okay, fine. We will revisit that in a later class. Let us move on to the bigger problem. benzene.
How does higher spin states work for metals and
It becomes complicated. It becomes more complicated. So, don't have to go to metals. Think of oxygen. I think even from a very preliminary discussion, we know that oxygen has a triplet ground state, right? Where does the triplet ground state arise from? These three wave functions, right? The next excited state is singlet. There are two singlet states. Now, that excitation is just a change in the spin wave functions. Okay. So, you do not even have to go that far. So, what I am trying to say is that these states that you get, do not think that different states arise only from the space part. They can also arise from the spin part. And there are numerous such examples in inorganic chemistry. I consider O2 to be an inorganic molecule also, so starting right from oxygen. Okay. If we get time, we will come to that.